In 1977, 3 mathematicians at the Massachusetts Institute of Technology discovered something that would quietly become the most important secret in the history of human civilization. They were not trying to build a weapon. They were not commissioned by any government. They were playing with prime numbers because prime numbers are strange and beautiful, and they wanted to see what would happen if you use them as locks. What they found was a mathematical trick, so precise, so geometrically elegant, that it would eventually hold up the entire digital infrastructure of the modern world. Banks, governments, military communications, medical records, nuclear command systems, all of it resting on a single asymmetry that 3 people discovered in a university building one afternoon in the 1970s. The asymmetry works like this. Take 2 prime numbers, each hundreds of digits long, and multiply them together. A computer does this in a fraction of a second. Now reverse the problem, take the result, and figure out which 2 primes produced it. Suddenly, you are in an entirely different universe of difficulty. For a number, the size used in modern encryption, the best classical algorithms would take longer than the current age of the universe to work backward through the math. Not a long time, longer than everything, longer than the stars themselves, have left to burn. Ron Rivest, Adi Shamir, and Leonard Adleman built a cryptographic system out of this asymmetry. They published the product as a public key. To decrypt, you needed the original primes. Nobody could find them. The mathematics would not allow it, not in millions of years, not before the heat death of the universe. They called it RSA, 3 letters that became the invisible foundation beneath the entire digital world. Right now, as you listen to this, that foundation has a crack in it. The crack appeared in a laboratory in Santa Barbara, California in 2019. It widened through 2024, and the fracture is now large enough that the most significant intelligence agencies on Earth have issued warnings, the kind of warnings that use words like immediately and timeline and migrate. Now, this is not a theoretical concern. The architecture of civilization is being undermined by something that most people have never thought about, and the machine doing the undermining operates according to rules so strange that even the physicists who built it find themselves staring into a world that does not resemble the one they grew up believing in. To understand what is happening and why it matters so much, we need to go to a room at Google in 2019 where a processor called Sycamore was given a problem, not a useful problem, not the kind that changes anyone's life, but a mathematical puzzle specifically designed to answer one question. Can this machine do something that no classical computer can do? Sycamore finished in 3 minutes and 20 seconds. The same task on the fastest supercomputer that existed at the time would have taken roughly 10,000 years. Let that sit for a moment. 10,000 years. That is the entire recorded history of human civilization. Every empire that rose and fell, every war, every cathedral built stone by stone, every book ever written, compressed into the time it takes to boil an egg. A physicist at the California Institute of Technology named John Preskill had a name for this moment. He called it quantum supremacy, not because the machine was faster, since faster implies the same road traveled at greater speed, but because this was a different road entirely, a road that classical computers cannot even find, let alone drive on. The world moved on. A pandemic arrived, elections happened, and most people forgot. But the physicists did not forget, because Sycamore had proven something much more important than a speed record. It had proven that the road exists, that a quantum machine can reach places where classical machines simply cannot go. The task was a toy, but the road was real. And if you could fix the one brutal engineering problem that kept it from scaling, you could drive that road straight into the wall that protects every secret on Earth. The problem was noise. A qubit, the quantum equivalent of a classical bit, is the most fragile object humans have ever tried to engineer. Think about that for a moment. We build skyscrapers in earthquake zones. We land robots on Mars. We split atoms and contain the results. But a qubit makes all of that look crude, because a qubit holds its information in a quantum state so delicate that a single stray photon, a vibration too small for any human instrument to detect, a thermal fluctuation without a name in everyday language, any of these can destroy it. Not corrupt the information, not degrade it, erase it entirely, gone. Like a soap bubble touched by a fingertip. And here was the nightmare. To solve harder problems, you need more qubits. But more qubits means more surfaces exposed to the environment, more opportunities for things to go wrong. Every qubit you add is another soap bubble in the cluster, another target for the universe to disturb. For decades, this was the wall. You could not build a useful quantum computer because the system drowned in its own noise before it finished thinking. In 1995, a mathematician named Peter Shor, and you will hear his name again very shortly, for a much darker reason, proved something important on paper. He showed that quantum error correction is theoretically possible, that you can design a system where adding more qubits actually reduces errors rather than multiplying them. The theorem was mathematically beautiful, and it sat on paper for 29 years because no one on Earth could build it. Then in December 2024, Google published results from a new processor called Willow, and the curve flipped. For the first time in the history of the field, more qubits meant fewer errors. 29 years of failed attempts, and the barrier gave way. Not in theory, in silicon, in a laboratory you could walk into and touch. The soap bubbles stopped popping. The machine could now grow, and a machine that can grow can eventually run any algorithm you feed it, including one very specific algorithm that has been sitting in the open literature for 30 years, like a loaded gun on a library shelf. The algorithm was built in 1994 by that same Peter Shor, working at Bell Laboratories in New Jersey. Bell Labs, the place where the transistor was invented, the place where the mathematical theory of information was born. Shor was not trying to build a weapon. He was curious about a math problem, a simple one actually. Take two numbers, multiply them together, easy. Now reverse it. Find the two original numbers from the product. Shor found a way to do this on a quantum computer in an afternoon, not by brute force, not by checking every possibility one after another the way a classical computer would, but by exploiting a property of quantum mechanics that allows the machine to walk every possible path simultaneously and cancel out the wrong answers through something called interference. We will get to how that works. What matters right now is what it means. Because that asymmetry, the gap between multiplication and factoring that RSA was built on, is not just a curiosity. It is the bridge your bank drives across, the bridge your government drives across, the bridge that carries every encrypted message your civilization has ever sent. And Shor's algorithm is a clean, elegant, mathematically proven way to collapse it. The algorithm has been published for 30 years. Anyone can read it. It is not classified, not hidden, sitting in plain sight, harmless only because no machine existed that could run it. Sycamore proved the road exists. Willow proved the machine can scale. The algorithm has been waiting, but here is where you might expect a backup plan, a second floor under the first. some other kind of mathematics, holding everything up in case RSA fails. You would expect this because no engineer builds a civilization on a single point of failure, except they did. In 1985, two mathematicians working independently, Neil Qubits in the United States and Victor Miller in Canada, developed something called elliptic curve cryptography. It looks different from RSA. It uses mathematical curves instead of prime numbers, runs faster, produces shorter keys. If RSA is a heavy iron padlock, elliptic curve cryptography feels like a sleek modern deadbolt. Different mechanism, different design, and surely a different vulnerability. Same vulnerability. Because Shor's algorithm does not attack RSA directly, it attacks the mathematical structure underneath RSA, something called the hidden subgroup problem. Elliptic curve cryptography sits on the same structure. The padlock and the deadbolt are the same metal, and the acid dissolves both. No second floor, no backup bridge. The entire digital world stands on a single assumption. Factoring large numbers is hard. Every protocol, every encrypted connection, every digital signature, every secure channel, all of it trapped behind that single assumption. When it collapses everywhere. Like pulling a tablecloth out from under every dish. On a table that stretches around the planet, you might think that at least gives us a race. The machine is not ready yet. We have time. We can swap the locks before the danger arrives, and that logic would be perfectly sound if the attack were starting now or in the future. It is not. The attack started years ago. There is a strategy in intelligence work that requires no quantum computer at all. It requires patience and hard drives. It is called harvest now, decrypt later, and it works exactly the way it sounds. You intercept encrypted traffic. You cannot read it, so you do not try. You simply copy it, all of it. You fill warehouses with hard drives containing gibberish that you cannot decode, and you wait. You wait for the quantum machine to mature. The moment it does, you feed the archive into it, and the gibberish turns into words. Think about that personally. Every encrypted email you sent 5 years ago, every bank transfer, every medical record that crossed a network, every private message. If it was intercepted and storage costs less per gigabyte than the coffee you drank this morning, it may be sitting in a vault right now, sealed and waiting for a key that does not exist yet, but will, patient as stone, certain as mathematics. In 2022, the United States National Security Agency released an advisory telling all national security systems to begin migrating to quantum-resistant encryption immediately. That word, immediately, carries weight when it comes from people whose job requires knowing where the threat actually stands on the timeline. You cannot re-encrypt the past. You can change every lock on Earth tomorrow, and it will not matter for anything already intercepted. The past is in the vault. The key is being assembled in laboratories right now. When it is finished, the vault opens backward through time, and every secret that ever crossed a wire becomes readable. Now, you are probably imagining a spy with a recorder, tapping a single cable, copying a few important files. That is not what this looks like. The global internet moves roughly 400 exabytes of data every single day. If you printed that out on paper, the stack would reach the sun every day and start over the next morning. Within that flood, there is a concentrated stream of encrypted traffic that carries real weight. Diplomatic back channels, military logistics, intelligence communications, financial clearing systems, energy grid commands, pharmaceutical research. The stream is a fraction of the total, but a fraction of a number that reaches the sun is still an enormous amount of material. The infrastructure to intercept that stream is not hypothetical, and it has existed since the early 2000s. fiber optic splitters, satellite intercepts, undersea cable monitoring, all feeding the same archive. Encrypted data does not rot. It does not degrade or expire. It sits in perfect mathematical fidelity, ones and zeros, exactly as they were the moment they were copied, waiting. Stretch that across 15 years of accumulation, and the value becomes difficult to comprehend. A single diplomatic cable revealing a negotiation position can be worth more than most people earn in a lifetime. A single military communication can redraw the balance of power across an entire ocean. There are not single cables in the vault. There are billions, layer upon layer of frozen history, and this is what makes it fundamentally different from every breach you have ever heard about. Every other major hack in history exploited a mistake, a software bug, a lazy password, a security patch that came too late. This one exploits the mathematics itself. The lock was not weak. The lock was perfect, and it is going to be opened anyway because someone built a machine that operates by rules the lock was never designed to withstand. Rules that do not belong to the world most of us grew up understanding. To see those rules, we have to go inside the machine, not through the wires or the refrigeration system, but all the way down to the physical object the machine is protecting and exploiting, a thing so alien to everyday experience that the physicist who understood it most deeply described the only honest reaction as confusion. His name was Richard Feynman, and he was exactly the kind of person you would expect to crack open the foundations of physical reality. A Nobel laureate who played bongo drums, picked locks at Los Alamos for entertainment, and made physics sound like a conversation between people who genuinely enjoyed thinking. In 1981, Feynman stood in front of an audience at the Massachusetts Institute of Technology and said something that sounded, at the time, like a joke. He said that if you want to simulate nature, if you want to build a computer that can model the way the physical world actually behaves, you cannot do it with a classical machine. Classical machines speak the wrong language. Nature, Feynman said, is not classical. And then he added a word that does not usually appear in physics lectures. He said, and this is an accurate quotation, "Damn it, nature is not classical, damn it." He was frustrated because he had spent decades in the quantum world, the layer underneath, the one you and I walk around in every day, and it played by rules that no classical computer could even represent, let alone calculate. A classical computer thinks in bits. A switch is either on or off, 1 or 0, that is it. Every calculation your laptop has ever performed is billions of switches flipping between 1 and 0 very quickly, but still just switches. A qubit is not a switch. A qubit is both 1 and 0 at the same time, not because we do not know which one it is, not as a metaphor for uncertainty, genuinely, physically, measurably, in both states simultaneously. This is a physical fact, confirmed every day in laboratories around the world for over 100 years. The first time you hear it, it should bother you. If it does not bother you, you have not fully understood what is being said. Feynman himself said that nobody truly understands quantum mechanics. The best you can do is get comfortable with the discomfort. The discomfort has a name. It is called superposition, and it was not discovered by theorists sitting in armchairs. It was discovered in 1922 by two experimentalists named Otto Stern and Walter Gerlach, working in Frankfurt, Germany, who shot silver atoms through a magnetic field and got a result that made no sense. The experiment was supposed to be straightforward. Heat silver atoms until they fly off in a beam. Send the beam through a magnetic field that is stronger on one side than the other. Classical physics predicts the atoms should spread out in a continuous smear, like paint sprayed at a wall. Instead, the beam split into two clean dots, not a smear, two clean discrete points, as if every atom had made a binary choice, up or down, with nothing in between, and no reason from classical physics that could explain why. Strange enough, but the real conceptual trouble came later, when physicists started asking what the atom was actually doing before it hit the detector. The answer, confirmed by a century of increasingly precise experiments, is that it was not doing either. It was not going up. It was not going down. It was not undecided in the way a coin is undecided before it lands. It was in both states simultaneously as a single physical reality. The act of measurement forced it to choose. Before that, there was nothing to choose between, because both options were equally real. Imagine a coin spinning in the air. While it spins, it is not heads and it is not tails. It is something else, a third state containing both possibilities. The moment it hits your palm, one answer emerges, but in the air, asking heads or tails is like asking whether blue weighs more than a Tuesday. The question does not apply to the situation. A qubit is a coin that never lands until you look at it. While it spins, it carries two answers at once. 2 qubits carry 4. 10 qubits carry 1,024. 30 qubits carry 1 billion. The growth is exponential, but carrying answers is useless if you cannot pull out the right one. You need a mechanism that selects the correct answer from the cloud of possibilities and discards everything else. That mechanism exists, and it was first demonstrated not by a physicist, but by a physician who was experimenting with light in his spare time. In 1801, Thomas Young cut 2 narrow slits in a barrier and shone light through them. On the wall behind the barrier, he expected to see 2 bright lines corresponding to the 2 slits. Instead, he saw a pattern, bright bands alternating with dark bands, spreading across the wall like the ripples from 2 stones dropped in a pond at the same time. This was interference. The waves of light passing through the 2 slits were overlapping, and where 2 peaks met, they amplified each other into a bright band. Where a peak met a trough, they canceled each other into a dark band. You can see the same effect in a bathtub if you tap the water in 2 places at once. 200 years later, this bathtub effect is the operational engine of quantum computing. Here is how. A qubit in superposition carries multiple answers at once. A system of 300 qubits carries more simultaneous answers than there are atoms in the observable universe. That is not poetry. That is arithmetic. 2 to the power of 300 is a number so large that writing it out would require more paper than exists on Earth. All of those answers exist simultaneously inside the machine. But if you simply open the box and look, the superposition collapses. You get one random answer out of the enormous pile, useless. So instead of measuring directly, you do something more careful. You make the answers interfere with each other. The wrong answers, like peaks meeting troughs in Young's experiment, cancel themselves out. They destroy each other. The right answer, like 2 peaks meeting, gets amplified, gets louder, rises above everything else. When you finally measure the system, the right answer is the one left standing. This is not a metaphor for how the machine works. This is the physical mechanism by which a quantum computer solves problems. It sends a computation down every possible path simultaneously, lets the paths interfere, and wave mechanics does the filtering. The machine does not search for the answer the way a classical computer searches, checking possibilities one by one. The answer emerges from the collision of all the wrong ones dying, and interference is not something only light can do. In 1961, Klaus Jonsson proved that single electrons fired one at a time through two slits build the same interference pattern. In 1999, Anton Zeilinger in Vienna pushed the demonstration further with molecules containing 60 carbon atoms, objects large enough to see under an electron microscope, walking through two doors at the same time and interfering with themselves. A quantum computer with 300 qubits processes 2 to the power of 300 paths simultaneously. That number dwarfs anything the physical universe contains. The paths interfere and produce a verified correct answer. So where is the computation physically happening? The resources do not exist in this universe. Either the answer is wrong, which it is not, or those resources are coming from somewhere we cannot see. A physicist named David Deutsch at Oxford University stared at this problem for years. Deutsch is unusual even by the standards of theoretical physics. He studied under John Archibald Wheeler, the man who coined the term black hole, and he was not interested in building computers. He was interested in what computers reveal about the structure of reality. In 1985, he published the first true quantum algorithm, not Shor's, an earlier and simpler one designed to prove a theoretical point. And the point was the question we just hit. A quantum computer solves problems that would require more operations than there are particles in the universe, and it solves them correctly. The answer checks out every time. Where did the work happen? Deutsch's answer is the one nobody wants to hear. The work happened in parallel versions of reality, not parallel in a poetic sense, not parallel as a metaphor for efficiency, parallel in the most literal, physically rigorous, mathematically precise sense available. The computation was distributed across branches of reality that we cannot see, cannot touch, and cannot directly measure, but whose existence is the only explanation consistent with a result that we can see, can touch, and can verify. Think of it as an audit. A company reports $10 billion in profit. You check the books. The company has one factory producing $1 million per year. The numbers do not balance. Either the report is falsified, or there are factories you have not found. In quantum computing, the report is real. The single factory is our universe. It does not have the resources, so either the result is wrong, and it is not, or there are factories somewhere else. Deutsch called them the multiverse, and he was careful to say this was not speculation. It was the only accounting that balanced the books. This is where the floor drops. You came to this story because of encryption, and you have arrived at a place where the device threatening your passwords works because reality is not one thing. It is many things, layered and branching, and the machine reaches into those layers and pulls out answers that any single layer could never produce alone. If that sounds like science fiction, hold that feeling for a moment, because what comes next is not a hypothesis. It is an experimental result. The universe was tested to see if it is what we thought it was. The universe failed the test. Deutsch did not invent the multiverse. He inherited it. The idea was born in the most unlikely place possible, a graduate student's dissertation that almost nobody read. His name was Hugh Everett III, Princeton University, 1957, 26 years old. His advisor was John Archibald Wheeler, the same Wheeler who would later mentor Deutsch. Everett was trying to solve a problem that had been gnawing at physicists since the 1920s. The problem was simple to state and seemingly impossible to answer. Why does a quantum system behave one way when you are not observing it, and a completely different way when you are? The standard answer, the one taught in every physics classroom at the time, was called the Copenhagen interpretation, championed by Niels Bohr, the most influential physicist of the era. Bohr's answer was this: when you measure a quantum system, the superposition collapses. One outcome becomes real. The rest vanish. Do not ask where they go. Do not ask what collapses the wave function. The question is meaningless. Shut up and calculate. Everett looked at this and said no. He said the mathematics does not require a collapse. Schrödinger's equation, the master equation of quantum mechanics, works perfectly well without adding one. If you simply let the equation run without inserting the collapse artificially, what happens is that every possible outcome occurs. Not one, but all of them. The universe does not choose a single outcome. It branches into every possible version, every measurement, every quantum interaction, every moment where a particle could go left or right. The universe splits into branches where it went left and branches where it went right. Both are real. Both continue. Neither is more fundamental than the other. Wheeler made Everett cut the paper in half. Bohr dismissed it in person. The physics community shrugged. Everett left academia, took a job at the Pentagon, never published another physics paper, drank heavily, and died of a heart attack at 51. His instructions were for his ashes to be thrown out with the garbage. They were. 40 years later, quantum computing arrived, and the only framework that could explain what it was doing was the one belonging to the man whose ashes went out with the trash. So what does it mean for reality to branch? Not as a thought experiment you entertain over coffee and then forget. What does it actually, physically, mathematically mean? The answer lives in a mathematical object called Hilbert space. In your everyday life, you can describe where you are using three numbers: how far left or right, how far forward or back, how far up or down. 3 dimensions. Hilbert space works the same way, but with vastly more dimensions. For a single qubit, Hilbert space has 2 dimensions. For 2 qubits, 4. For 3, 8. For 300 qubits, 2 to the power of 300 dimensions. A space so vast that no physical analogy can hold it. In Hilbert space, superposition is not magic. It is just a location. A qubit in superposition is a point in a 2-dimensional space, leaning partly toward 0 and partly toward 1. When you measure it, you are projecting that point onto one axis or the other, like shining a flashlight on a ball hanging in midair and looking at its shadow on the floor. The shadow falls left or right. The ball was never on the floor. It was always above it, in a space with more room than the shadow could capture. According to Schrödinger's equation, when you measure a qubit, you do not simply project the ball. You, the observer holding the flashlight, also enter Hilbert space. You become entangled with the qubit. In the full mathematical description, there are now 2 versions of you, one who saw the shadow fall left and one who saw it fall right. Both versions are equally real points in Hilbert space. Neither is the original, neither is the copy. They are branches of the same mathematical object, like a tree that forks. Every quantum interaction is a fork. Every fork is permanent. The branches do not rejoin. They cannot see each other. This is not philosophy added to the physics. This is the mathematics running without additions. No collapse inserted by hand. No mystical observer required. Just the equation running and branching, and a machine in a cryogenic chamber solving problems that no single branch has the resources to solve alone. Not everyone accepts this picture, and the argument against it is not simple or obviously wrong. It is an old argument, older than quantum computing, older than Everett. It goes back to a hotel in Brussels in 1927, where the greatest physicists alive nearly destroyed decades of friendship over the question of what reality fundamentally is. The Solvay Conference, of October 1927 brought 29 physicists into a hotel in Brussels, and 17 of them would go on to win Nobel Prizes. Einstein was there, Bohr was there, along with Werner Heisenberg, Erwin Schrödinger, Paul Dirac, Max Born, Max Planck, Marie Curie, and Ernest Lawrence. If you erase that guest list from history, modern physics would not exist. They gathered to discuss the new quantum mechanics, and they could not agree on what it meant. What does a quantum particle do when no one is looking at it? Does it even exist between measurements? Bohr's position was radical in its restraint. The mathematics works. Asking what the electron is doing when you are not looking is not a scientific question. There is nothing there until you look. Stop asking and calculate. Einstein hated this, not because the mathematics was wrong, but because it meant abandoning the idea that the universe exists whether you look at it or not. He famously asked whether the moon ceases to exist when nobody is looking at it. For an electron, the Copenhagen answer is genuinely, there is nothing there until you look. They fought for 30 years. Einstein designed thought experiments designed to trap Bohr, to find a contradiction in the theory. Bohr found the escape every time. Einstein could not land the decisive blow. Then in 1935, he thought he had it. He co-authored a paper with Boris Podolsky and Nathan Rosen that was meant to be the kill shot. The paper described a scenario so strange, so fundamentally offensive to common sense, that Einstein was certain it would prove quantum mechanics was incomplete. He was certain it would show that there must be hidden variables, deeper rules underneath the quantum randomness that restored a sensible, local, deterministic universe. He called the scenario spooky action at a distance, intending it as an insult. He had no idea he was describing the actual architecture of reality. Einstein, Podolsky, and Rosen published 4 pages in Physical Review in May of 1935, and those 4 pages may be the most consequential in the history of physics. The argument went like this: create 2 particles in a shared quantum state, what we now call an entangled pair, then separate them and send one to New York and the other to Tokyo. According to quantum mechanics, neither particle has a definite state until measured. Both are in superposition, but the moment you measure the particle in New York and find it spinning up, you instantly know the particle in Tokyo is spinning down. Instantly, not after a light speed delay. Instantaneously, regardless of the distance between them. Einstein said this was absurd. Information cannot travel faster than light. That is the foundation of relativity. Either something is traveling faster than light, which is impossible, or the particles had definite states all along. The way gloves shipped in separate boxes to different cities already have their handedness before you open either box. You open the box in New York, find a left glove, and instantly know Tokyo received the right one. No spooky action required, because the gloves were always left and right, and you simply did not know which was which. This was the hidden variables argument. Predetermined results. Quantum mechanics not wrong, but simply incomplete. Einstein was sure of it. He was wrong. Proving it took 29 years. Nobody could figure out how to distinguish between the 2 possibilities, a universe with hidden variables versus a genuinely non-local universe, until a soft-spoken physicist named John Stuart Bell sat down with a pencil and found the one number that would be different. Bell was born in Belfast in 1928 to a working-class family, his father a horse trader. He was the first person in his family to stay in school past 14. He studied physics at Queen's University Belfast, then moved to CERN in Geneva, where he spent his days designing particle accelerators and his evenings thinking about the foundations of quantum mechanics. His colleagues considered the evening work a hobby. They were wrong. It was the most important work anyone at CERN would do that decade. Bell was obsessed with the Einstein-Podolsky-Rosen argument, not because he sided with either Bohr or Einstein, but because everyone was arguing philosophy when they should have been arguing mathematics. Neither side had proposed an experimental test in 29 years. Bell broke the impasse with a single equation, published in 1964 in an obscure journal, 6 pages long. The idea was this: if hidden variables exist, there is a mathematical ceiling on how strongly 2 entangled particles can be correlated. Measure one in New York, the other in Tokyo. Repeat thousands of times, and the statistics cannot exceed a specific number. Bell calculated that number precisely. If quantum mechanics is correct, the statistics blow past the ceiling. The mathematics predicts it clearly. For the first time, you had an actual test, not philosophy. A specific number? Below the ceiling, Einstein wins, and you can sleep comfortably. Above the ceiling, the universe is non-local, and the word distance does not mean what you have always assumed it means. The experiment was extraordinarily difficult to perform, and it would take 20 years before anyone could do it. The man who did it was a French physicist named Alain Aspect, working at the University of Paris, who ran the experiment in 1982. He created pairs of entangled photons, sent them in opposite directions, measured their polarization at random angles, chosen at the last possible instant so that neither particle could influence the other through any signal traveling at or below the speed of light, and collected enough data to run the statistics. The number was above the ceiling, not slightly, not ambiguously, clearly, cleanly, unmistakably above Bell's limit. The correlations between the 2 photons were stronger than any hidden variable theory could allow. The particles were not like gloves. The universe you grew up believing in, the one where things have definite properties, whether or not anyone is looking at them, failed the test. The particles did not carry predetermined answers. The correlation was not a product of shared history. It was something else, something that happened at the moment of measurement across an arbitrary distance with no signal passing between them. Aspect's experiment had small technical loopholes that a determined skeptic could work around. So others followed: John Clauser, Anton Zeilinger, each closing a different gap and tightening the experimental constraints around local realism. In 2015, Zeilinger's group performed the first fully loophole-free Bell test. Every escape route sealed. The number was above the ceiling, not close. In 2022, the Nobel Prize in Physics went to Clauser, Aspect, and Zeilinger. The universe is non-local, not a debate, not a hypothesis, an experimental result, replicated thousands of times across 4 decades, with every loophole closed. 2 particles separated by any distance are connected by something that does not travel between them. The word here and the word there do not carry the meaning you have always assigned them. Einstein called it spooky. He was right about the spooky part. He was wrong about everything else. Now you could file non-locality under strange facts about physics and move on with your life. Except for one thing, the machine we have been talking about since the beginning of this story does not just coexist with non-locality, it runs on it. Entanglement is not a curiosity that quantum computers happen to be built alongside. Entanglement is the wiring. In 1993, Charles Bennett at IBM described quantum teleportation, not the teleportation of matter, but of a quantum state from one location to another, using an entangled pair as a bridge. The measurement destroys the state locally. The information reappears at the destination as if it jumped through a tunnel with no inside. In 2017, a Chinese satellite called Messius demonstrated this across 12,200 kilometers. Entangled photons from orbit to ground. The particles behaved as one object across empty space. Inside a quantum computer, entanglement does something even more fundamental. Qubits do not work alone. The power of the machine comes from qubits being entangled with each other so that the state of one is locked to the state of another. When you entangle 30 qubits, you do not have 30 separate coins spinning independently in the air. You have one object with 2 to the power of 30 faces all spinning together, all interfering together, all collapsing together into a single result. Entanglement is what turns a collection of individual qubits into a single unified quantum system. Without it, you have a very cold, very expensive box of broken switches. And there is another application of entanglement that loops back to where this story started. Quantum key distribution creates a communication channel that is physically impossible to eavesdrop on because intercepting an entangled particle changes its state. The act of listening destroys the message. The same non-locality that breaks the old locks builds new ones that cannot be broken by any machine, now or in the future. The thing that kills the old world is the foundation of the new one. But there is a deeper question hiding underneath all of this. By now, the inventory of strange facts should be genuinely unsettling. Superposition is real, confirmed every day for a century. Interference is real, and it powers the machine that threatens your encryption. Entanglement is real, stamped with a Nobel Prize in 2022. Non-locality is an experimental fact, with every loophole sealed. The multiverse remains the only accounting that balances the books. Not one of these is a fringe idea. Together, they are the operating manual of physical reality as we currently understand it. And that manual describes a world nothing like the one you woke up in this morning. So why does the world feel normal? You walk outside and the ground is solid. The sky is one color. Your coffee is either hot or cold, never in both states at once. You do not experience superposition. You do not notice entanglement. You have never looked at a chair and seen it in two places simultaneously. The quantum world, with all its strangeness, its branching, its non-locality, its refusal to commit to a single answer, seems to be confined to a tiny invisible basement beneath the world you actually inhabit. It is not confined. It is everywhere. It is the floor and the walls and the ceiling. The reason you do not see it is not that it stops at some scale. The reason is that something is actively hiding it from you. Something is taking the raw quantum weirdness of reality and smoothing it into the clean, solid, single-answer world. Your brain has evolved to navigate. The first clue to how this works comes from the oldest, strangest, most conceptually infuriating experiment in all of physics. You already know it, the double slit. We told half the story. The half we left out is what Feynman called the only mystery. Add a detector at one of the slits, something that tells you which slit each particle passes through. Something extraordinary happens. The interference pattern vanishes. Without a detector, you get interference, both slits, the beautiful alternating bands. Place a detector to know which path was taken, and the interference disappears. One slit, one path, classical behavior. As if the universe runs two entirely different programs, one for when you are looking and one for when you are not, and the act of looking flips the switch. This has been tested with every quantum object anyone has tried. The result is always the same. Observation changes the outcome. Not observation as in a conscious mind necessarily, observation as in information becoming available somewhere in the universe. The universe behaves differently depending on whether information about the event exists. That sentence, if you sit with it long enough, rearranges the way you think about everything. It gets considerably stranger. In 1978, John Archibald Wheeler proposed an experiment that should not be possible. He called it the delayed choice experiment. What if you wait until after the particle has already passed through the slits before you decide whether to measure which slit it went through? Think carefully about what that means. The particle has already traveled. It has already passed the barrier. If it went through both slits without being observed, it is already interfering with itself. The event is in the past. Wheeler proposed that it does not matter when you decide. Choose to place the detector after the fact, and the particle will behave as if it had known your decision in advance. If you choose to observe, no interference, one slit. If you choose not to observe, interference, both slits, even though the particle passed through the slits before your decision existed. For 29 years, this was a thought experiment, the kind of thing physicists debated at conferences and then went home and tried to stop thinking about. Then in 2007, a team led by Vincent Jacques in France built the apparatus. They used single photons and a device that randomly decided after the photon had already entered the apparatus whether to measure which path it took. The result confirmed Wheeler's prediction exactly. The photon behaved as if it knew the future when the detector was switched on, after the photon had already passed the slits. The decision made after the event changed the nature of the event, not retroactively, in some loose philosophical sense. Physically, measurably, repeatedly, the data was clean. The photon does not know the future. What is happening is stranger. The photon does not have a history until the measurement creates one. The past is not fixed. It is contingent on what information becomes available in the present, and then it gets even stranger still. You can erase the information, and when you do, the universe changes its mind. In 1982, two physicists named Marlan Scully and Kai Druhl proposed what they called the quantum eraser. Start with the double-slit experiment and place a detector at one slit so you know which path the particle takes. The interference pattern vanishes. Classical behavior. Now here's the twist. What if you erase the information from the detector? Not the particle, not the screen, but the information itself. What if you destroy the record of which slit the particle went through after the particle has already hit the screen? Their prediction was that the interference pattern would return, retroactively visible in the data from particles that had already been detected. In 2000, researchers at the University of Maryland built the experiment, entangled photon pairs. One photon hit the detection screen. The other was sent through a series of optical elements that either preserved or erased the witch path information, arriving at its own detector after the signal had already been recorded. When the information was preserved, no interference appeared. When the information was erased, interference reappeared in photons that had already been detected and already recorded. The act of erasing information about the past changed the pattern the past had left behind. The universe does not care about observers. It does not care about consciousness or detectors or human intentions. It cares about one thing. Does the information exist? If the information exists, classical behavior. If it does not, quantum. If you create the information and then destroy it, reality switches back as if the information had never existed at all. This tells us something profound and uncomfortable. The fundamental currency of reality is not matter. It is not energy. It is information. The universe is not made of stuff. The universe is made of what is known about stuff. and the rules change depending on whether the knowledge exists anywhere. If you are still holding on to the idea that there is one reality out there, solid and objective, and the same for everyone regardless of who is looking, one more experiment takes that away. Eugene Wigner proposed a thought experiment in 1961. Your friend is inside a closed laboratory. She measures a quantum particle in superposition and sees a definite result: spin up. For her, reality has delivered an answer. But you are outside. You have not opened the door. From your perspective, the entire laboratory is still in superposition. Your friend, the particle, the notebook she wrote the result in, all of it remains in a quantum state. For you, the experiment has no result yet. Who is right? Quantum mechanics says both of you. Not approximately. Both of you are applying the correct laws of physics to the information available to you, but your facts are mutually exclusive. She says spin up. You say both outcomes are still possible. You cannot both be describing the same objective reality unless there is no single objective reality to describe. For 58 years, this was a thought experiment, a reason to drink after physics seminars. Then in 2019, Massimiliano Proietti and a team at Heriot-Watt University in Edinburgh built it. Entangled photons, multiple observers, a direct test of whether different observers' results could be made consistent within a single objective framework. They could not. The paper was published in the journal Nature Physics. Observer-independent facts may not exist, not philosophically, experimentally, measured, published, replicated. The universe may not have a view from nowhere, only views from somewhere, and those views do not have to agree. This is the deepest point of the spiral. We came here following a machine that cracks encryption, and we have arrived at a place where the word real does not mean what it used to mean, but chairs still hold you up, coffee is still hot, the world still functions exactly as your experience tells you it should. If all of this is true, something must be packaging the quantum chaos into the stable, ordinary-looking world you experience every moment. Something is, and it has a name, decoherence. A German physicist named Heinz-Dieter Zeh first glimpsed the answer in 1970. Zeh was an outsider. His ideas were ignored for over a decade. The physics community was so committed to the Copenhagen interpretation, to the rule that you should not ask what happens between measurements, that anyone who tried to answer the question was treated as professionally irresponsible. Zeh answered it anyway. He showed that a quantum system does not exist in isolation. It interacts with its environment, and the interactions are continuous and unavoidable. A photon bounces off the system and carries away a trace of its quantum state. An air molecule collides with it and takes another trace. Thermal vibrations pass through the surrounding material and spread the traces further. Each interaction is tiny, insignificant on its own, but each one leaks a sliver of information about the superposition into the surrounding world. Once the information leaks, the superposition does not collapse. It drowns. Imagine you are standing in an empty cathedral. You whisper a word, every consonant sharp and precise. Now imagine the same whisper in a crowd of 8 billion people, all talking at full volume. Your vocal cords vibrate the same way, but no one hears you. Not because you stopped, because your signal dissolved into the noise. It is not gone, it is lost. That is decoherence. A qubit in superposition is the whisper. The environment is the crowd. The moment the qubit interacts with anything, the superposition leaks into the surroundings and becomes undetectable. Not destroyed, but diluted past the point of recovery. From our perspective, it looks as if the qubit chose one state. It looks classical. This is why chairs are solid. Not because quantum mechanics stops at the scale of a chair. It never stops. A chair is trillions of atoms, constantly bombarded by photons and thermal noise, and the decoherence time is so short, it might as well be zero. The superposition drowns before you can blink, and this is what a quantum computer is fighting against every moment it operates. The cryogenic chamber, the vacuum, the shielding, all of it exists for one reason: to keep the crowd silent long enough for the whisper to finish its sentence. A quantum computer operates at 15 millikelvin. That is 15 thousandths of a degree above absolute zero, colder than the vacuum of deep space, colder than anything that occurs naturally anywhere in the observable universe. At that temperature, thermal vibrations nearly vanish. Air molecules are gone because there is no air, only vacuum. Electromagnetic noise is suppressed by layers of shielding that a bomb shelter would envy. The qubit sits inside this fortress of silence, isolated from the rest of the universe as completely as human engineering can manage. And even then, it only stays coherent for a fraction of a second. A quantum computer builds a tiny pocket of reality where superposition survives long enough to complete a calculation. The engineers are not building a faster calculator. They are building a room where the mask comes off for a few microseconds before decoherence slams the door shut. Every advance in the field is a battle to keep that door open a fraction longer. Willow did not just reduce errors. It extended the duration in which the machine can think before the universe interrupts. The physicist Wojciech Zurek, who formalized decoherence mathematically in 1981, was not satisfied with the simple version of the story. He asked a question nobody else was asking. If the environment destroys superposition, why does it always leave the same survivors behind? Why do chairs come out solid every single time instead of dissolving into some other configuration? The answer he arrived at, published in 2009, he called quantum Darwinism. The name is not a metaphor. It is a precise analogy to biological natural selection. Zurek showed that when a quantum system interacts with its environment, the environment does not erase superposition blindly. It selects certain states. The ones robust against photon bombardment and thermal noise survive. Everything else dissolves. What remains, what Zurek called pointer states, is the only version of quantum reality that the classical world ever gets to see. Your chair is solid not because solidity is a fundamental property of the universe. Your chair is solid because the quantum state corresponding to solidity is the one that survives decoherence. Among the trillions of possible quantum states the atoms in your chair could occupy, the overwhelming majority dissolve on contact with the environment. The one that persists, the one that gets copied and amplified and spread across every photon bouncing off the surface, is the state you call solid, brown, wooden, here. It won, not because reality chose it, because everything else lost. This changes what the classical world actually is. It is not the ground floor. It is not the foundation. It is the top layer, the residue, the survivors of a selection process happening at every scale, at every moment, in every atom, trillions of times per second. Underneath it, the full quantum reality is still churning, branching, interfering, doing all the strange things it does. You just cannot see it because the environment has already selected the winners by the time any information reaches your eyes. Physicists looked for the boundary, the size at which quantum behavior stops and classical behavior begins. They did not find it. In 1999, Zeilinger's group in Vienna sent molecules of carbon-60 through a double-slit experiment. Carbon-60, also called Buckminster fullerene, 60 atoms arranged in the shape of a soccer ball. a molecule large enough to see under an electron microscope. They fired these molecules one at a time through the slits. The interference pattern was clean and unmistakable. A molecule made of 60 atoms walked through 2 doors at the same time and interfered with itself. In 2011, Marcus Arndt, also in Vienna, pushed the demonstration further. His team demonstrated interference with molecules containing over 430 atoms, complex organic molecules that by any everyday standard are stuff, tangible, real, with a shape and a chemical formula. They were in superposition, both paths at once, interfering with themselves. The record keeps climbing. Every few years, a larger molecule, and the same result each time. The quantum world does not know it is supposed to stop at some boundary. The line between quantum and classical does not appear because it does not exist. There is no wall. There is only decoherence getting faster as objects get larger, drowning the signal before it can be detected. The signal is still there. There is no size limit on superposition. The equations do not discriminate. The only thing preventing you from seeing a building in 2 places at once is that the decoherence. Time is so short the superposition dissolves before a single photon can carry the information to your eye. The world is not classical. The world is quantum, moving too fast for you to catch. The machine in the cryogenic chamber slows it down long enough to see what it looks like underneath. A surface that is not a floor, a mask, and the machine that lifts the mask can also do something else with what it sees. Remember what Feynman said in 1981 when he stood up and declared that nature is not classical. He was not simply complaining. He was pointing at a specific problem that classical computers could not solve. The problem was simulation in the physics sense, predicting how a quantum system will behave by modeling every interaction between every particle. Why does this matter? A molecule is a quantum system. The atoms in a molecule are held together by electron bonds, and those electrons obey quantum mechanics. If you want to predict the behavior of a new molecule, a drug candidate, a catalyst, a superconductor, you need to model those bonds accurately. A classical computer can handle small molecules, hydrogen, helium, a few atoms, but the number of quantum states grows exponentially with every atom you add. By the time you reach around 50 atoms, the number of states exceeds what any classical computer can store, let alone calculate. 50 atoms is a molecule smaller than a grain of sand. This is not a limitation of current computers. It is a fundamental limitation of classical computation itself. You cannot simulate a quantum system with a classical machine because the classical machine does not have access to the same physics. It is like trying to predict how water flows by pushing coins around on a table. The coins do not flow. They are the wrong kind of object. A quantum computer uses the right kind of object. Its qubits obey the same laws as the electrons in the molecule: superposition, entanglement, interference. The machine does not calculate the behavior of the molecule. It mirrors it. It becomes a small version of the same physics, and the answer emerges from the machine the same way it emerges from nature, by letting the quantum states evolve and interfere until the result appears. In 2020, Google simulated the electronic structure of a chain of 12 hydrogen atoms, a simple system that pushes classical methods to their limits. Alan Asparuguzik, a chemist who has spent his career at the intersection of quantum computing and molecular science, describes this as the real revolution. Not cracking codes, but modeling molecules. New drugs designed by machines that think in the same language as the molecules themselves. New materials with properties that no classical method could predict. new catalysts for chemical reactions we could never model accurately enough to optimize. The entire field of chemistry has been using mathematical approximations since its founding because no exact method existed. It is about to get a machine that does not approximate, it solves. The same machine that threatens every lock on Earth could redesign the molecules in the medicine you take. The thing that splits the old world open is the same thing that assembles the new one, because it speaks the language the universe is actually written in. But speaking a language is not the same as only speaking it. The same superposition that powers computation also powers measurement. A qubit is the most sensitive object humans have ever built precisely because it is the most fragile. Every stray photon, every thermal whisper, every gravitational ripple nudges it. That fragility is the enemy inside a quantum computer. But fragility is not a flaw. It is a feature with two faces. Put that same sensitivity to work as a sensor, and it becomes something entirely different. An ear pressed against the wall of reality, hearing things no classical instrument can detect. An atomic clock that uses superposition to measure time with a precision that would not drift by a single second in 15 billion years, longer than the universe has existed. A quantum gravimeter that can feel the presence of a buried tunnel from the surface of the road above it, not by digging, but by listening to the shape of the gravitational field with an entangled atom that notices what classical sensors would miss entirely. A quantum magnetometer that can detect the electrical signal from a single neuron firing inside a living brain, not through surgery, but through the extraordinary sensitivity of a qubit tuned to magnetic fields, so fine that one nerve cell's tiny electrical pop is enough to move the measurement. This is the same physics, the same superposition, the same entanglement. The thing that breaks your encryption also measures time more precisely than anything else in the observable universe. The thing that cracks the bridge also maps the inside of your brain without touching your skull. And here is the part that should completely twist your expectations. That fragility, the very thing that makes a qubit so difficult to maintain inside a computer, is also the thing that makes quantum information impossible to steal without detection, because you cannot touch a qubit without changing it, and you cannot copy it at all. This is not a design choice, not a security feature that some clever engineer added. It is a law of physics. In 1982, 3 physicists working independently, William Wouters, Wojciech Zurek, and Dennis Deeks, proved what is called the no-cloning theorem. You cannot duplicate an arbitrary quantum state, not with a better machine, not with more energy, not with technology 1,000 years more advanced than ours. The universe will not permit it. The prohibition is baked into the mathematics, the way the speed of light is baked into relativity, not a wall you can climb with a taller ladder. The absence of a direction called up, what does this mean for the harvest? What happens to harvest now? Decrypt later when copying becomes impossible. RSA, the bridge, the lock, the entire system cracking under the weight of Shor's algorithm was built on a mathematical assumption. Factoring is hard. That assumption held for 50 years. It is about to fall. But the no-cloning theorem is not an assumption. It is a physical law. Physical laws do not fall. They do not get revised by a smarter algorithm or broken by a faster machine. They are the rules and not our rules. The rules. The old lock was built on mathematics. The new lock is built on physics. And that difference is the difference between a wall that might crumble under the right circumstances and a wall that cannot exist in a broken state. Stephen Wiesner, one of Feynman's students, saw this in 1970. He proposed quantum money, currency that physically cannot be counterfeited, because counterfeiting is copying, and copying is what the universe forbids. The idea sat in a drawer for decades. Now the technology exists to implement it, but even unbreakable locks live inside physical limits. There is a genuine cost to computation, not a metaphorical cost, a fundamental physical cost assessed by the universe on every calculation ever performed. In 1961, Rolf Landauer at IBM proved that erasing one bit of information produces a minimum amount of heat, not as a consequence of inefficiency, but as a matter of physics. Information is physical. The formula is compact. Boltzmann's constant times temperature times the natural logarithm of 2. The hotter the environment, the more it costs to forget. Charles Bennett showed in 1973 that you can avoid this tax by never erasing, by designing computations that are reversible. But deferral is not escape. The debt accumulates in a different form because reversible computation requires infinite memory, and memory is matter, and matter costs energy. Even before Landauer, Leon Brillouin showed in 1962 that there is a maximum speed at which any physical system can process information, set by the energy it contains. Seth Lloyd, at the Massachusetts Institute of Technology, later calculated what he called the ultimate laptop, a computer operating at the physical limit of the laws of physics, 10 to the power of 50 operations per second, a number beyond comprehension and still finite, still inside a cage. A quantum computer harnesses interference, entanglement, and superposition, and that combination makes it exponentially more powerful than any classical machine. But exponential power is still power inside a cage. The multiverse might be the engine. Entropy is the brake. The universe gave us superposition with one hand and wrote the invoice with the other. And inside these limits, the quantum computer will eventually break RSA. That is not a question. It is arithmetic. The machine is scaling. The algorithm has been waiting for 30 years. The old lock will fall. The only question is whether the new lock will be in place before it does. The new lock exists. It is not theoretical. It has a name, a published standard, and a deployment deadline. In 2016, the National Institute of Standards and Technology launched a competition, an open call to mathematicians and cryptographers from every country. Build an algorithm that a quantum computer cannot break. Can you design a lock that Shor's algorithm cannot dissolve? The competition ran for 8 years. Dozens of candidates entered, and teams from universities, corporations, and intelligence agencies spent years trying to break each other's submissions until most fell and a few survived. The survivors are built on what mathematicians call lattice problems. Imagine standing in a grid of points in three-dimensional space. Finding the shortest path between 2 points is straightforward. Now imagine the same grid stretching into 500 dimensions. The shortest path is still there. The mathematics guarantees its existence, but finding it, actually calculating which route is shortest through a forest of 500-dimensional intersections, is a problem that neither classical computers nor quantum computers can solve efficiently. Shor's algorithm, the acid that dissolves RSA, does not work here. Different mathematical structure, different terrain entirely. The acid hits the lattice and nothing happens. In 2024, NIST announced the winners. Crystals Kyber for key exchange, Crystals Dilithium for digital signatures. The names sound like science fiction, but the mathematics underneath them has been tested, attacked, and stress tested for nearly a decade by the best cryptanalysts alive. The new standard is published, the new lock is cut, and the migration has begun. But migration is not a switch you flip. Every server on Earth, every satellite in orbit, every embedded chip in every medical device and weapon system, all of it runs on RSA or elliptic curve cryptography. Some cannot be updated. The hardware predates the threat, and those systems have to be physically replaced from scratch. This process takes decades. While the decades pass, the harvest continues, new secrets flowing through old pipes, the margin shrinking every day. The race is a slow, grinding, narrowing corridor against a clock that does not care about budget, constraints, or the fact that the engineer who designed your building's security system retired 15 years ago, and nobody has the credentials to update it. Whether the new lock gets installed before the old one breaks is a question nobody can answer with confidence right now. The arithmetic is uncomfortably close. Step back for a moment, not from the mathematics, but from the timeline. In 1900, Max Planck introduces the quantum as a mathematical trick to fix an equation that did not work. By 1922, Stern and Gerlach discover it is a physical reality. In 1935, Einstein tries to eliminate it with the EPR argument and accidentally describes the architecture he was trying to disprove. In 1957, Everett proposes the multiverse and is pushed out of academic physics. In 1964, Bell finds the experimental test. In 1982, Aspect proves that reality is non-local. In 1994, Shor writes the algorithm, and then the acceleration. 2019, Sycamore. 2022, the Nobel Prize. 2024, Willow. 125 years. What kind of species does this in 125 years? What kind of organism goes from a mathematical trick to a machine that reaches into the basement of physical reality in the time it takes a redwood tree to grow? We are not necessarily the most intelligent species to have lived on this planet. We are the first to reach into that basement, not just on Earth, but as far as we can determine, anywhere we have ever looked. We have found no signal from the sky, no artifact on Mars, no footprint on any moon of any planet around any star we have ever observed. As far as we can tell, we are the first piece of matter in the observable universe that looked at the rules governing its own existence and deliberately built a tool that exploits them. We did not just discover that reality has a basement. We built a machine that works down there, and what we found in the basement is not what we expected. We expected a faster computer. We found a universe that is non-local, possibly branching, governed by information rather than matter, and quite possibly lacking a single objective reality that all observers share. We found that the classical world, the solid, sensible, single-answer world you wake up in every morning, is not the foundation. It is the top layer, the residue, the mask. The machine that threatens your bank account is the same machine that revealed the mask. And now there is one last question the machine might eventually answer. The strangest one, the one about us. The question is simple, and it might be unanswerable, but the machine we have been building might be the first instrument that can take a serious run at it. If observation changes reality, and we are the observers, what are we? Think back through the experiments we walked through together. In the double-slit experiment, observation collapses the interference pattern. In the delayed choice experiment, a future observation retroactively shapes the past. In the quantum eraser, destroying information restores quantum behavior. In the Wigner's friend experiment, two observers see mutually exclusive realities, and both are physically correct. Every time we peeled back a layer, The observer was standing at the center of the machinery, not as a passive witness, as an active ingredient in the outcome. Roger Penrose thinks this means something about consciousness. Penrose, the Oxford mathematician who shared the 2020 Nobel Prize in Physics for his work on black holes, has spent decades arguing that human consciousness is not a classical process. In 1989, he published a book in which he proposed that awareness arises from quantum effects in the brain, not from neurons firing like transistors, from something operating at the boundary between quantum and classical, in the same territory where decoherence turns superposition into the solid world. Stuart Hameroff, an anesthesiologist at the University of Arizona, gave Penrose's intuition a physical address. Microtubules, tiny protein structures that form the internal scaffolding of every cell. Hameroff and Penrose proposed that quantum superposition occurs inside them and that conscious experience corresponds to the moment of decoherence. The theory is called orchestrated objective reduction, or ORCA-OR. 30 years of criticism and refinement, not proven, not disproven. In 2015, Matthew Fisher proposed a different mechanism involving nuclear spins of phosphorus atoms in Posner clusters, with coherence times potentially long enough for quantum processes to influence neural activity. Younger, more speculative, but specific enough to be falsified, which in science is the highest compliment a theory can receive. None of this is settled. We do not know whether consciousness is a quantum process, but the question is no longer purely philosophical. It has predictions that can be tested. It has mechanisms that can be modeled, and the machine that might test them is the same machine that started this story by threatening to break every lock on Earth. Remember what the machine does. It simulates quantum systems, molecules, materials, chemistry that classical machines cannot touch. But a microtubule is a quantum system, the same kind of system you carry in every cell of your body. A Posner cluster is a quantum system. A neural network operating at the boundary of decoherence is a quantum system. If Penrose is right, or if Fisher is right, or if someone we have not yet met proposes a third mechanism closer to the truth, then this machine is the first instrument that could simulate consciousness at the level where consciousness might actually operate, not model it, not approximate it with statistics the way a classical neural network does. Simulate it, run the same physics. Let the qubits do what the microtubules do, or what the phosphorus spins do, and see what happens. See if awareness emerges from the mathematics the same way interference emerges from the double slit, not because you programmed it to, because the physics produces it. We built this machine to break a lock that had held for 50 years. That was the stated purpose. That was the funding justification. That was the reason governments poured enormous resources into error correction and cryogenic chambers and the long grinding race between the old lock and the new one. And the machine might turn around and answer a question that has haunted every conscious being since the first one opened its eyes. What am I? Why am I aware? Is awareness a product of computation, or is it something the universe does at a level deeper than computation can reach? The gun that was built to break the bridge might turn out to be a mirror, and the face looking back might be the first clear image we have ever had of ourselves. Let us return to the bridge, not the metaphor, but the real thing, the mathematical structure that holds the digital world together. RSA, elliptic curve cryptography, the single point of failure that protects every secret your civilization has generated since the invention of the internet. The crack is real. The machine is scaling. The harvest has been ongoing for years. And the new lock exists, but the migration is painfully, dangerously slow. These are facts, not speculation, unfolding right now in laboratories and server rooms and intelligence agencies while you are listening to this. The same world where your coffee is getting cold and your phone is buzzing with something you should probably check, but something changed. When we started, the crack in the wall was the point. The danger was the point. The machine was a threat, a weapon aimed at the foundation, and that has not changed. The harvest is real. The vulnerability is real. The arithmetic of migration versus machine maturation is genuinely tight. But you followed the crack down through the wall, through the mathematics, through the machine, into the qubit, into superposition and interference and entanglement, into the multiverse, into delayed choice and the quantum eraser, and the experimental death of objective reality, into decoherence and quantum Darwinism, and the disappearance of the boundary between quantum and classical, into the fundamental limits of computation itself, into the question of what consciousness is and whether the machine that breaks your password might also explain your mind. The crack in the wall was not a failure. It was a door, not a door we designed or expected, a door that opened because we built a machine to break a lock and discovered that the lock was attached to something much larger than a vault. It was attached to the architecture of reality. When the machine forced the lock, it did not just open the vault, it opened a view. Here is what you see through the door. The universe is not what it looks like. The solid, singular, common sense world that your senses deliver to you every morning is a surface. Underneath it, reality is non-local. Two particles separated by a galaxy are connected by something that does not travel between them, and the word distance does not apply. And if distance is an illusion, then the universe is far more deeply connected than it appears, which means it can branch. Every quantum event is a fork. Every fork is permanent. The version of you that turned this off 20 minutes ago is, mathematically, as real as the version still listening right now. And if it branches, what determines which branch you experience? Not matter, information. The past is contingent on what information exists in the present. And if information governs reality, then objective reality, the kind that is the same for everyone, regardless of who is looking, may not exist at all. Because two observers with different information can hold mutually exclusive facts and both be correct. And if objectivity falls, what is left? A residue. What you see is what survived. Solidity is not a fact. It is a survivor. And the device that showed us all of this is the same one about to break the lock on every digital secret you own. The telescope and the weapon are the same object. What reveals the basement is what breaks the floor. Was any of this supposed to happen? The engineers wanted a faster computer. The cryptographers wanted a better lock. The physicists wanted to simulate molecules. Nobody set out to discover that reality has a mask. But the universe does not care what you set out to discover. It operates on the actual rules. And the actual rules turned out to be stranger than anyone involved was prepared for. So what do you do with this? You woke up this morning in a world that felt solid. You drank something. You checked your phone. The screen was bright, and the floor was under your feet, and the walls of your room were exactly where you left them. Nothing about your morning suggested that the universe is non-local, that reality might branch every time a particle makes a transition, that the past can be reshaped by erasing information in the present, or that the chair you are sitting in is not truly solid, but is instead the quantum state that happened to survive a selection process running trillions of times per second in every atom beneath you. Nothing about your morning suggested any of that. and nothing about your tomorrow will either. That is not because the science is wrong. Everything we walk through together is real, confirmed, replicated, Nobel Prizes awarded. The universe really is that strange. But strangeness does not reach up. Decoherence ensures that the noise of 10 to the power of 23 particles drowns every quantum whisper before it reaches the scale where your eyes and your coffee operate. You will never see your chair in two places at once. The basement is sealed not by a lock, but by the sheer volume of the crowd. Your life does not need to change because of what you learned today. Knowledge is not danger. It is weight. Your bank account is still there. Your locks still hold for now. The harvest is real, but it is a problem for cryptographers and governments and systems engineers. The migration to post-quantum encryption will happen. It will be slow. It will be messy. Some things will break. Most will not. The new lock is built on physics, not mathematics, and physics does not bend. But something did change. Not in the world. In you. You know now. You know that the machine your government is racing to build and racing to defend against is not a faster calculator. It is a device that operates in the basement of reality, using rules that the world you see does not appear to follow, pulling answers from a space that might contain more versions of the universe than there are atoms in any single one of them. You know that the floor you are standing on is not the bottom. There is a layer underneath, and underneath that another, and the further down you go, the less the world looks like the world. Things become less solid, then less singular, then less local, and finally less objective, until what you are looking at does not resemble the surface at all. The deeper you dig, the more the universe looks like something made of information rather than stuff, something that behaves differently depending on whether anyone is keeping records, something that might not have a single story at all, only billions of stories, branching, interfering, selecting, and producing the thin, stable, classical surface that your senses evolved to navigate. You did not need to know this. You could have gone your entire life without learning that a silver atom passes through a magnetic field in two directions simultaneously, or that a photon's behavior changes based on a choice made after it has already arrived, or that two observers can disagree about a fact and both be right. You would have been fine. The sun would rise on schedule. The people you love would still be there when you got home. But you know now, and on the other side of the discomfort, there is something else. Not terror, not nihilism, not the grim resignation of a species that discovered it is standing on a trapdoor. Something better than that. The kind of wonder that comes from realizing the thing you live inside is incomprehensibly more complex, more layered, more deeply structured than anything you were equipped to imagine. The kind that does not shrink you, that locates you. You are here, a biological organism made of carbon and water, a product of quantum chemistry, so intricate that no classical computer will ever simulate the molecule that carries your genetic code. Standing on a planet that condensed out of a dust cloud, governed by the same quantum mechanics that powers the machine in the cryogenic chamber, looking up at a sky full of stars whose light traveled as both a wave and a particle to reach your retina. You are not separate from this. You are this. You are quantum mechanics walking around asking questions about itself. And you built a machine that can look at itself in the entire history of matter in the observable universe, stretching back 13.8 billion years. No piece of that matter has ever, as far as we can tell, constructed a device that deliberately exploits the quantum foundations of reality to perform computation. Rocks did not do it. Stars did not do it. Galaxies did not do it. But you did. It breaks locks. It reads the basement. It might one day simulate the process that produces the experience of being you. It is dangerous and extraordinary, and the fact that it exists at all is, if you allow yourself to sit with it for a moment, the most improbable thing in the visible universe. The wall has a crack. That is where we started. The crack is real. The machine is real. The harvest is real. The race between the old lock and the new one is real, and it is close. These things matter. They will shape the next 20 years of security, diplomacy, intelligence, and trust. People in rooms you will never enter are working on it right now and will keep working on it tomorrow. But the crack goes deeper than anyone planned. It goes through the mathematics, through the physics, through the architecture of reality, all the way down to a basement where the rules are not what we thought they were. And the device that opened the crack did not just reveal a threat, it revealed a world. You are still here. The floor is still solid. The coffee is cold by now, but the mug is still in your hand. The morning is still doing what mornings do. Nothing about your life needs to change because of what you heard. But the next time you set a cup down on a table and hear the small, solid, reassuring sound of ceramic meeting wood, know that underneath that sound, underneath the atoms in the ceramic, and the atoms in the wood, and the atoms in the air that carried the sound to your ear, there is something else, something non-local, something branching, something that behaves differently depending on whether information about it exists anywhere, something that might not have a single story, something that a machine in a cryogenic chamber colder than the space between the stars is only just beginning to read. If you found this exploration of the universe's deepest architecture worth your time, leaving A-like helps others find their way to the same questions. And if you want to keep going deeper, subscribing means the next door opens right when it should. You are fine. You are here. The world is holding, and underneath it, the universe is doing something extraordinary.